And I will. So what I want to talk about is rigorous computation of invariant measure. In which sense? In the sense that what we would like to do is to approximate, compute some description of some interesting invariant measure in a dynamical system up to a given explicit error. So in which sense I mean to compute an invariant measure? To compute an invariant, the idea is that you have your space X where the dynamics is. You consider the space of, for example, a space of probability measure which defined in the space, and then you consider a distance, and then, for example, you can consider this notion of distance, which is quite general. You can take two probability measure mu1 and mu2 and test both the measure on all the function having Lipschitz constant 1, and this gives you a notion of the of a distance between the two measures, which is related, is not immediate from the formula, but is related to the cost of transporting one measure to the other. And well, this is a notion which works for general measure, but if you, for some reason, you are looking to regular measure having some density, you can consider the L1 distance or the L infinite distance, and so there will be several notions of approximate a measure up to a given error in some distance. And in this talk, if time permitting, I will start with measure having density, and then at the end I will talk about a fractal, a system having an interesting measure having fractal behavior. So the approximation there will be done up to the Wasserstein distance. And in this framework, to rigorously approximate, for me, it will mean that we have the system. The system will have many invariant measures. Maybe we are interested to physically interesting measures, which are often the most regular one. And we decide a notion, and we notion of distance we are interested in, and we try to develop an algorithm that, given the system, will give us the interesting measure I want to compute up to a given explicit error. And not only I want to talk about the possibility to have algorithms, but really implementable algorithms. And we will see some example of computation and implementation. Of course, the idea of having the error explicitly comes from a mathematical interest, because if you do something like this, when you perform a computer experiment, the output will be like a theorem. Is a statement on some quantitative property of the system, which will be proved like with a computer-aided proof. So in some system I could say, like, you give me one map on the interval which has an absolutely continuous invariant measure. I run the computer, and then I can state something like the entropy of the system is between this number and this number, and this is like a theorem. Okay, this is a mathematical interest of the question, but since we are in an interdisciplinary framework, what I can say about more applied interests of the thing? Well, I could say we are going to more reliable simulation or forecasting of systems, but I have to say, and you will see that the system for which we can really run the algorithm until the end are very, very simple, quite far from the ones which are used in application, for example, in forecasting of weather and things like that. But the method we use, apart of the exact estimation of the error, are related to transfer operator, and these are used indeed in meteorology, and so maybe it can be interesting also for the more applied scientists to see how things are defined and how we can work with this. On the other hand, something more interesting maybe for application is that I can work with simple system, but I can give some exact result. And this system maybe can be used as a benchmark for statistical estimator. Like, for example, we want to have try several estimator of entropy of time series. You can try it on a given system for which I can give some exact value for the entropy, and this can really be done with this method. Okay, so let's look what we do to have this rigorous approximation. The main thing to look at is the transfer operator. We say we want to consider a dynamical system. So we have maybe the pointer works. Okay. So for me, a dynamical system will be a discrete time dynamical system. So there is a space where the dynamics is, and the dynamics is generated by iterating a certain function. These dynamics induce a dynamics also on the space of measure defined on the space, because as the dynamics moves points, you can from this you can define a dynamics which move measure in the same way as it moves the points. And a formal definition is this one, but you can think that the measure is made of many small masses, and all the small masses are moved by the dynamics to other points, and altogether this moves the whole measure. And but anyhow, the formal definition is this one, and what I would like to say is that, okay, you have the dynamics, then you have an operator acting on measure, and this probability measure on the space is not a vector space, but you can enlarge your space to measure with sign or complex valued measure. And in this case, the operator is linear, and the invariant measure are fixed point of the operator. So we will work to approximate some fixed point of some operator. Of course, given a map, there can be a lot of invariant measure, but as I was saying before, often the most interesting one are the most regular one. So sometimes we will restrict to a subspace, and where maybe there is only one invariant measure, and we will compute this invariant measure more easily. So since, for example, seeing this problem, so you have a kind of big linear operator, and you want to compute the fixed point. If you want to do this from an abstract point of view, there are results saying that if a fixed point is isolated, then there is an algorithm to compute it up to any given approximation, and then you are, I think, we were naturally led to conjecture that given a computable dynamical system, in the sense that this notion can be formalized, but and I will not enter into the formal definition, but a computable dynamical system is a dynamical system where the map can be simulated at any precision by a computer. So you can think that if you have a computable dynamical system and you want to compute the invariant measure, there may be a computable dynamical system is if the system has some physical measure, maybe it's computable. You can conjecture something like that, and we tried to prove a result like that, and after a while we discovered that we proved the opposite. There are we found a contra-example. There are computable systems in the sense that the system a computer can simulate the orbits, the behavior of for example, the pre-image of open set and everything with any given approximation. But this computable system has no computable invariant measure up to small error in the vastest time distance. So maybe it's the largest notion of approximation we can take. So I will not enter in the detail, but it's just to say there are some theoretical computer scientific sophistication in the problem. Of course, this example, if someone is interested, I can explain later, is an example you will not find in application. I don't think you will find it in application because it contains numbers which are semi-computable but not computable. So it contains some, it's a kind of pathological example, but this example exists. So there is some abstract computability sophistication in the problem. But okay, if you forget this and you want to go to simple example and to real life problems, what you do to compute this invariant measure? I said the invariant measure are fixed point for the transfer operator. The idea is that the first idea, and it was implemented in many ways in many kind of algorithms, is that you can approximate the real transfer operator by some, for example, finite rank operator. We will call it L delta, where delta is a number telling you how good is the approximation. For example, it can be, you can choose a grid of size delta and approximate the fixed point of the real operator with fixed point of the approximated operator. But of course, you need some result telling you that some quantitatively, if this is near to this, how the fixed point of the approximated one and the real one are far each other. Of course, this is a very natural question. It's a question about stability of fixed point. And of course, there are many results on stability of fixed point. I have to say that when we started to do this, we wanted to apply this result, and indeed they can be applied. But we were a little bit uncomfortable with this because the results which are known are very strong. They can approximate the whole spectral picture, but they need strong assumption and some estimation which is not so trivial to be done. So we try to make a simplified argument, which is this one, and So this is a kind of simplified fixed point statement, which is in some sense a little bit optimized for computation, and I will try to explain why. The statement is like this. Suppose you restrict your interest to a subspace of measure with sign on your space, and you consider the restriction of the transfer operator to this space. You can think about like this is the space of absolutely continuous measure, and you want to look for absolutely continuous invariant measure. Suppose you have this operator acting on the restricted space and an approximating operator acting on the same space. Suppose that f is a fixed point for the real operator and f delta is a fixed point for the approximated operator, and consider the space of measure, let's say absolutely continuous invariant measure, but this works in any normed vector space, such that the total measure of the space is 0. So these are the 0 average densities if you think about absolutely continuous invariant measure. And suppose that the two operators, when applied to the fixed point of the real operator, are near each other. Of course, you can say, how can you suppose this if you don't know f? But we will find argument to make a kind of a priori estimation for this part. This can be done in some way if you know something about the system. But philosophically, this means something like, okay, L delta is a good approximation of L. Then suppose you can find an N, a big N, such that the approximated operator applied to a vector in the 0 average space is a contraction whose contraction rate is better than 1/2. 1/2 is not very important here. You can choose any number smaller than 1, but let's choose 1/2. And suppose that the approximated operator restricted to V has defined Ci as the norm of the approximated operator restricted to the space of 0 average measure. Then the error you make, the distance between the two fixed points, is bounded by this sum, which contains the quality of the approximation, all these coefficients, and the number of coefficients is this number that you find. You have many coefficients if you need many iterations to contract the 0 average space. So this is a stability result. What is the good part of the stability result? Is that the good part is this one. Provided you can estimate this, and here you need something a priori. You have to make some analysis and estimate this a priori. Then the other estimations are on the approximated operator, and the approximated operator can be like a matrix. So this n will be computed by the computer, and this for people who are more expert on dynamical system is like an estimation of decay of correlation at a finite resolution, which will be made by the computer, which is often the hardest part. The decay of correlation is harder than other things, and the good point of this statement is that this part will be a posteriori estimation which will be made by the computer on the finite rank operator, which is a matrix. So let's see how to apply the result in a simple class of example. Suppose you want to approximate in L1. So here now the distance, all the distance will be in L1. Sorry, this is 1. And how to do this a priori estimation? For example, if you have some information on the regularity of f, and you have some way to estimate the norm of the difference of the two operators considered as an operator from, for example, you have an estimation of the regularity of f in BV. We will show how you can easily have this in a class of dynamical system. And suppose you have an estimation for this norm, then you can bound this with the product of these two, and this can be computed explicitly as a function of the grid. I will specify better later. And so you have this, and the rest of the things will be done by the computer. The same idea can be applied in several situations. So what is important is that to recall is that to do this you need a regularity estimation for f and some approximation estimation for the operator. Let's see quickly a class of example where everything can be done easily. Maybe everybody knows this class of example. Let's consider a class of maps on the interval which are piecewise expanding. In which sense piecewise expanding? The derivative is always bigger than, let's say, bigger than 2. You can relax to 1, but okay, for some reason we will see later. So the derivative of there is an expansion rate which is big enough. The system can be discontinuous, can also have some infinite derivative somewhere, and you have many branches made like this, and there is some regularity on the map, like the inverse of the derivative of the map has bounded variation. Then in this case you can prove an inequality like this, which is called the Lasota-York inequality. It can be proven in many situations, saying in some sense that the transfer operator is regularizing with respect to the bounded variation norm. That is, if you take a starting density and you take the image 5 minutes, okay. I have this and then some example, and then let me just show the picture of the fractal thing. So I was saying that this inequality says that you can bound the variation of iterates of a given starting density. So, and you can estimate all the coefficients in some way starting from the description of the system. If you iterate many times and use many times this inequality, you will have a bound on the variation of the invariant measure. And so this is, in this class of map you have this says that in this class of map you have an estimation for some regularity estimation for f. Let's see what we consider as an approximated operator. This is very famous, is the Ulam discretization. In this discretization is maybe the simplest one to imagine. You replace your system with a Markov chain. You divide your space into cells, and you look the measure of and you look how cells are sent to each other, and you recall the measure of which is sent. Suppose you take this cell and you say, a part of this cell is sent here, and you recall the measure. A part of this cell is sent to this cell is sent to another cell, and so on and so on. And with all the transition measure, you make a Markov chain. If you do like this, you can estimate this operator norm easily in function of the coefficient of the Lasota-York inequality, and so you can bound this difference. And well, and this operation can be made in several examples. So the idea is the algorithm will be like this. You compute the Ulam approximation, you compute the approximated operator, you compute the n such that the approximated operator contracts the zero average measure space, and then you have an estimation for the error, which is the sum I was showing before. There is n summands, but okay. What I want to say is that it's possible to prove that the algorithm, this algorithm in this case, can approximate measure up to any given approximation, because the problem is that what if n grows very fast when delta goes to 0? If this happens, you cannot let the error go to 0, but you can prove that n will grow at most like the logarithm of the inverse of the size of the partition. So the algorithm works. And okay, of course, when you want to implement all these things, you have to, if you want a real computer-aided proof, a real rigorous experiment, you have to be careful in the implementation. This is quite complicated, but we use the interval arithmetics. I don't know if you know what it is, but in case it's something to have rigorous bound on the error you make, because in the computer there are rounding errors and there are many errors that accumulate when you do long computation. This is a way to manage all the error, and there are libraries to work with this. So let me, of course, starting from an invariant measure, you can also compute, for example, the Lyapunov exponent of the system. If this is easy when the system is one-dimensional. And let me show 3 examples where we implemented the algorithm. This is a piecewise expanding map with 4 branches. Let me just show, this is a picture of the invariant measure, and I show this only to say, so here the important thing is that if you take like 1 million of small interval, with this algorithm you get an L1 error which is smaller than this number, and then you have estimation for the entropy. The same procedure can be applied to maps with indifferent fixed point. These are systems whose dynamics is much more complicated to be studied than the system having a uniform expansion, because there is no Lyapunov inequality and there are many other complications. But still, you can using invariant cones, you can have a regularity estimation for the invariant measure, and then with another approximation inequality for the operator, you can do exactly the same procedure and obtain a statement about the entropy of the system, and a description of the invariant measure, which is diverging here because there is the neutral fixed point. Another example I want to talk about is a Lorentz-like map, because then, well, how much time I have? No. So the next step is to go to more complicated system which are piecewise hyperbolic, and they contain direction of contraction. In this case, you will not have absolutely continuous invariant measure, but you will have some measure with fractal support. An interesting class of example are the example which comes from the very famous Lorentz system, and they come as a first return map on a certain section. These are systems which preserve a foliation, but the foliation is contracting, and on the horizontal direction you have expansion, and you have a behavior which is like a piecewise expanding map. So here the computation of the measure can be done in a kind of, you can disintegrate. The idea is to disintegrate the measuring on the leaves, then compute the marginal by the expanding map, and then use I almost finished, and then use the contraction to estimate the error up to on the Wasserstein distance. Well, this I will not. If someone is interested, I can I can explain what we really did. But this is a work in progress. This is a picture of what we have. What we obtained is that to a certain resolution, this is the attractor and this is the invariant measure. Here there are some zoom, and let's say using this integration and the properties of the Wasserstein distance, you can also face this kind of problems. Of course, these are very simple model compared to what is used in real application, but this is something we are doing now. So I think I can stop here. Thank you.
Stefano. So yes, comments or questions? Remarks? Yes, please.
Did I understand correctly that you can approximate the invariant measure of the Fourier map for any exponent?
Not for any exponent. That was an example in the sense that a problem here is that you want to the computation really go to the end. If the exponent is too big, you have a long increasing of the time it takes to contract, because you have to wait until the space of zero average measure is contracted enough. And this will be slow in this system because this system has polynomial decay of correlation, and it depends on the exponent. So this is for the moment this can be done quite easily. The exponent is 1 plus 1 over 8, but if you increase it, the n you get is very big, and so I don't know, but it takes. What I mean is that in general the idea should work, but it takes a very long time if the exponent is big.
Okay, thank you.
All of a sudden the spectral gap popped up, so maybe there's some stuff that I don't know and that you can explain to me quickly what the connection of the Lasota-York inequality and the spectral gap is.
In general, there are theorems saying like if you have a system with the Lasota-York inequality and some technical assumptions are satisfied on but you have to decide on which space you want to consider your transfer operator and so on and so on. In general, if you have the Lasota-York inequality, then you have something near to the spectral gap. But here you don't have. In this example, and you don't have the spectral gap. And then if you have the spectral gap, you have exponential decay of correlation and many other good things. Does it answer to? I can show there are several theorems. There is a framework of statement for this kind of questions.
Okay, thank you very much.
Thank you.